Voyager 1 is the fastest object humanity has ever launched beyond the solar system. It is traveling at approximately 17 kilometers per second relative to the Sun. This sounds fast. In a single second, it covers 17 kilometers, the length of a small city. In a minute, it travels more than 1,000 kilometers, roughly the distance from London to Rome. In a day, it covers about 1.5 million kilometers. In a year, it covers about 538 million kilometers, more than 3 times the distance from the Earth to the Sun. And yet, at this speed, the journey to the nearest star system beyond our own, Alpha Centauri, 4,037 light-years away, would take approximately 76,000 years. No human alive today will see Voyager 1 arrive at any star. No human alive in 10,000 years will see it. No human alive in 50,000 years will see it. The civilization that receives any signal from Voyager at a stellar destination will be so far removed from us in time that we have no framework to imagine what they might be like, or whether the concept of receiving a signal will have any meaning to them at all. This is the fundamental problem of human spaceflight beyond the solar system. The universe is ancient. Light, the fastest possible signal, permitted by the known laws of physics, takes 4.37 years to travel to the nearest star. Our fastest spacecraft move at about 0.006% of the speed of light. The gap between what we can currently achieve and what we would need to achieve to visit another star within a human lifetime is not a small engineering gap. It is a gap of several orders of magnitude. But the question of tonight is not what we can do now. It is what we could theoretically do given our best understanding of physics, and what that would mean for how far a human being could travel in a single lifetime of perhaps 80 to 100 years. The answer to that question is more interesting and more surprising than most people expect. Let your breathing settle comfortably, in and out. The question we are exploring tonight is one of the great open questions of the human future, and it will take the entire richness of modern physics to answer it properly. There is no rush. Let the ideas arrive gently, one after another, like quiet revelations. The first obstacle to fast interstellar travel is the rocket equation. In 1903, the Russian schoolteacher and mathematician Konstantin Tsiolkovsky derived an equation that expresses the relationship between a rocket's change in velocity, the speed of its exhaust gases, and the ratio of its initial mass with fuel to its final mass without fuel. The Tsiolkovsky rocket equation is deceptively simple in form, but brutally constraining in practice. To increase a rocket's velocity by an amount equal to its exhaust velocity, you need the rocket to be about 63% fuel by mass at launch. To increase velocity by twice the exhaust velocity, you need about 86% of the mass to be fuel. 3 times, 95%. 4 times, 98%. The exhaust velocity of the best chemical rockets, burning hydrogen and oxygen, is about 4 kilometers per second. To reach even 1% of the speed of light, 3,000 kilometers per second, using chemical rockets, you would need a fuel-to-payload ratio that is not merely impractical, but absurdly beyond any conceivable engineering. The mass of fuel required would exceed the mass of the observable universe many times over. Chemical rockets, which have taken us to the moon and sent probes to the outer solar system, are fundamentally incapable of reaching even the lowest speeds relevant to interstellar travel within a human lifetime. This is not a problem of insufficient engineering effort. It is a fundamental consequence of thermochemistry. The chemical bonds in hydrogen and oxygen simply do not store enough energy per kilogram of fuel to propel a payload to the required speeds. To go faster, we need fundamentally different energy sources. The next step up in energy density is nuclear fission. The atomic bomb demonstrated that nuclear fission can release energy many millions of times more efficiently per unit mass than chemical combustion. A nuclear fission rocket, in which a nuclear reactor heats a propellant such as liquid hydrogen to extremely high temperatures and expels it through a nozzle, could achieve exhaust velocities of perhaps 8 to 10 kilometers per second, roughly twice those of the best chemical rockets. This would substantially improve performance over chemical propulsion, but would still be utterly inadequate for interstellar travel. The more ambitious proposal using fission is Project Orion, a concept developed in the 1950s and 1960s by a group of physicists, including Freeman Dyson and Theodore Taylor. The Orion concept involved a large spacecraft propelled by the sequential detonation of nuclear bombs at the rear of the vehicle. Each explosion would be absorbed by a massive pusher plate, connected to the spacecraft by shock absorbers, and the momentum of the explosion would accelerate the ship forward. The Orion concept was studied seriously and found to be technically feasible. Theoretical calculations suggested that an Orion ship could reach speeds of 3 to 5% of the speed of light, enough to reach Alpha Centauri in about 90 to 150 years. This is within the range of a multi-generational mission, if not a single human lifetime. Project Orion was ultimately canceled, in part because of the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. But the concept demonstrated that nuclear pulse propulsion is not science fiction. It is an engineering approach that the physics of the 20th century showed to be feasible, limited primarily by political and practical considerations rather than fundamental physical constraints. Let your breathing be slow and easy. The stars are far away. But the question of how to reach them is not a question that physics forbids. It is a question that engineering and time and ingenuity might one day answer, and exploring the range of possibilities is one of the most fascinating exercises in the application of real science to real ambitions. Nuclear fusion, the process that powers the sun and all other stars, offers far greater energy density than fission. In fusion, light atomic nuclei, such as hydrogen isotopes, are forced together at extremely high temperatures to form heavier nuclei, releasing substantial energy in the process. The energy released per kilogram of fuel in a hydrogen fusion reaction is about 3 to 4 times greater than in a fission reaction, and about 10 million times greater than in a chemical reaction. A fusion rocket could theoretically achieve exhaust velocities of several percent of the speed of light, sufficient to reach Alpha Centauri in a few decades. The British Interplanetary Society studied one specific design in the 1970s called Project Daedalus, a 2-stage fusion rocket burning pellets of deuterium and helium-3 ignited by electron beams. The Daedalus design was calculated to reach Alpha Centauri in about 50 years, accelerating to about 12% of the speed of light. It would be an unmanned flyby mission, not a crude round trip, and it would require enormous quantities of helium-3, which is rare on Earth but potentially available in the atmospheres of gas giant planets like Jupiter and Uranus. A follow-on study called Project Icarus, conducted from 2009 onwards by volunteers from the British Interplanetary Society and other organizations, refined the Daedalus concept and explored alternative approaches, all based on fusion propulsion. The conclusion of these studies is that fusion propulsion, if fusion ignition can be reliably achieved and sustained, could plausibly enable interstellar travel to the nearest stars in human-relevant timescales on the order of 50 to 100 years of travel time, which is within the range of a long human lifetime or a 2-generation mission. The challenge is that controlled nuclear fusion, sustaining a fusion reaction and extracting net energy from it, has been an active research goal since the 1950s and has not yet been achieved commercially. Progress has accelerated in recent years, with both government-funded projects like ITER in France and private companies like Commonwealth Fusion Systems reporting significant advances. But even optimistic projections place commercial fusion power decades away, and a fusion rocket engine would be an additional technological challenge beyond simply generating fusion power. Ion drives represent a different approach to propulsion, one that has already been demonstrated in space. Ion drives accelerate charged particles, typically xenon ions, using electric fields, and expel them at very high velocities, producing thrust. The exhaust velocity of ion drives is much higher than chemical rockets, typically 20 to 80 kilometers per second, meaning they are far more fuel efficient. The NASA Dawn spacecraft, which orbited both Vesta and Ceres in the asteroid belt, used ion propulsion. The Hayabusa 2 mission to asteroid Ryugu used ion drives. The drawback of ion drives is their very low thrust. While they are extremely fuel efficient, the thrust they produce is tiny, typically measured in millinewtons, compared to the hundreds of kilonewtons or meganewtons of a chemical rocket. Ion drives can accelerate a spacecraft continuously for months or years, gradually building up substantial velocity, but they cannot produce the rapid acceleration needed to escape a gravity well quickly. For a spacecraft already in space, starting from a depot in orbit, an advanced ion drive, or a more powerful variant called a Hall effect thruster, or a variable specific impulse magnetoplasma rocket, could potentially accelerate a payload to higher speeds than any chemical rocket, but still far short of what interstellar travel requires. Solar sails represent yet another approach, one that requires no fuel at all. A solar sail is a large, thin, reflective surface that generates thrust by absorbing and reflecting photons from the sun. While the pressure of sunlight is extremely small, a large enough sail can generate enough thrust to accelerate a very lightweight spacecraft over time. The Japanese Icarus spacecraft, launched in 2010, was the first to demonstrate solar sailing in interplanetary space. Solar sails have the advantage of requiring no propellant, but their thrust decreases with the square of the distance from the sun, making them ineffective in the outer solar system and useless in interstellar space. The Breakthrough Starshot Initiative, announced in 2016 and backed by physicist Stephen Hawking and investor Yuri Milner, proposes a radically different version of the sail concept, laser laser-propelled light sails. Instead of using sunlight, laser sails would be pushed by an enormous laser array on the ground or in orbit, beaming focused light at a tiny ultra-lightweight sail carrying a miniaturized payload. The laser provides far more photon pressure per unit area than sunlight and can maintain its intensity over long distances, unlike sunlight which falls off with distance. Breakthrough Starshot's calculations suggest that a gram-scale laser sail could be accelerated to about 20% of the speed of light in a matter of minutes by a sufficiently powerful laser array, reaching Alpha Centauri in about 20 years. The engineering challenges of laser sails are formidable. The laser array required would need to emit about 100 gigawatts of power, comparable to the total electrical generating capacity of a large country, all focused on a sail a few meters across thousands of kilometers away. The sail would need to be extraordinarily thin and reflective and heat-resistant, dissipating the enormous power of the laser beam without being vaporized. The pointing accuracy required to keep the laser focused on the rapidly accelerating sail would be extraordinary, and the payload that could be carried by a gram-scale craft is only a few grams, enough for cameras, sensors, and a transmitter, but not a human being or even a significant scientific instrument package. But the concept is physically sound. There is no fundamental physics objection to laser propulsion. The Breakthrough Starshot team includes Nobel laureate Saul Perlmutter and other serious scientists, and the project has produced substantive technical research. If the engineering challenges could be solved, which is a very large if, laser sails could be the fastest achievable physical objects in human history, reaching 20% of the speed of light. Antimatter propulsion is the most energetically efficient form of rocket propulsion allowed by known physics. When a particle of matter meets its corresponding antiparticle, both are annihilated and converted entirely into energy, primarily in the form of gamma rays. This conversion is described by Einstein's equation E equals mc squared. The energy released per kilogram of matter-antimatter annihilation is about 100 times greater than nuclear fusion and about 10 billion times greater than chemical combustion. An antimatter rocket in which matter-antimatter annihilation products are directed rearward to provide thrust could in principle achieve exhaust velocities approaching the speed of light and could accelerate a spacecraft to a substantial fraction of the speed of light. The problems with antimatter propulsion are equally formidable. Antimatter is produced in particle accelerators at a rate of nanograms per year and at enormous cost, currently estimated at about $60 trillion per gram. Storing antimatter requires magnetic traps that keep it away from ordinary matter indefinitely, a technology that currently works for microscopic quantities for short periods. And the gamma rays produced by proton-antiproton annihilation are extraordinarily difficult to direct into a beam for thrust purposes. Despite these challenges, antimatter propulsion remains a genuine theoretical possibility rather than merely science fiction, and it defines the upper limit of what is achievable with known physics for rocket propulsion. Now we arrive at the aspect of this question that is most surprising, most counterintuitive, and most wonderful: the effect of special relativity on travel time. As we discussed in our exploration of the universe, Einstein's special relativity shows that time passes more slowly for a moving observer than for a stationary one, and this effect, called time dilation, becomes dramatic at speeds close to the speed of light. Let your breathing be slow and easy as we work through what this means. At 10% of the speed of light, time dilation is small but measurable, about 0.5% slower than for a stationary observer. For practical purposes, a journey of 4.37 light-years to Alpha Centauri at 10% of the speed of light would take about 43 years of travel time as measured by both the ship and Earth, which is within a human lifetime. The time dilation effect is not significant at this speed. A person who left Earth at age 30 would arrive at Alpha Centauri at about age 73, having traveled 4.37 light-years. Earth would have aged about 43 years in their absence. At 50% of the speed of light, time dilation becomes significant. The Lorentz factor at this speed is about 1. 15, meaning time passes about 15% slower on the ship than on Earth. A journey of 4.37 light-years at 50% of the speed of light would take about 8.7 years of Earth time, but only about 7.6 years of ship time. A person who left Earth at 30 would arrive at Alpha Centauri at ship age 37.6, while Earth has aged 8.7 years. In a single lifetime of 80 years, at 50% of the speed of light, a traveler could cover about 58 light-years of Earth measured distance and about 50 years of ship time. That would put stellar systems like 55 Conchorei, Tau Ceti, and perhaps 24 of the nearest star systems within reach of a single lifetime. At 90% of the speed of light, the Lorentz factor is about 2.3. Time on the ship passes at less than half the rate it does on Earth. A 4.37 light-year journey takes about 4.9 years of Earth time, but only about 2.1 years of ship time. In 80 years of ship time, at 90% of the speed of light, a traveler could cover approximately 184 light-years of Earth-measured distance. That encompasses thousands of star systems. A significant volume of the Milky Way centered on our solar system, and includes many stellar regions of great scientific interest. At 99% of the speed of light, the Lorentz factor is about 7.1. Time on the ship passes at about 1/7 the rate it does on Earth. In 80 years of ship time, a traveler could cover approximately 567 light-years of Earth measured distance. A region of 567 light-years radius around the Sun contains an extraordinary number of star systems, including some of the most spectacular nebulae, open star clusters, and diverse stellar populations within our galactic neighborhood. The Orion Nebula, one of the nearest and most active stellar nurseries, is about 1,344 light-years away, somewhat farther than this range. At 99.9% of the speed of light, the Lorentz factor rises to about 22.4. In 80 years of ship time, a traveler could cover about 790 light-years of Earth measured distance. This begins to approach the scale of the Orion Nebula and other prominent nearby features of the galaxy. At 99.99% of the speed of light, the Lorentz factor is about 70.7. In 80 years of ship time, the traveler covers about 5,660 light-years. This is beginning to be a significant fraction of the width of the Milky Way's stellar disk. At 99% of the speed of light, the Lorentz factor rises to about 707. In 80 years of ship time, the traveler covers about 56,700 light-years, which is more than half the diameter of the Milky Way. The galactic center, about 26,000 light-years away, could be reached in about 37 years of ship time at this speed, and at speeds of 99.99999% of the speed of light, with a Lorentz factor of about 2,236, a traveler could cover about 179,000 light-years of Earth measured distance in 80 years of ship time. This is enough to travel from one side of the Milky Way to the other and back with room to spare. At these extreme speeds, the universe itself shrinks dramatically from the traveler's perspective. The distances contract, the time dilation compounds, and in principle, a sufficiently fast traveler could cross the observable universe in a human lifetime. But it is essential to be clear about what this means. The time experienced by the traveler is compressed. For the people they left behind on Earth, the time is not compressed. The traveler who crosses the Milky Way at 99.99% of the speed of light in 40 years of ship time has spent 26,000 years away from Earth by Earth's reckoning. When they arrive at the galactic center, everyone they knew is dead. Every civilization they left is ancient history. The Earth may be fundamentally different. The communication delay alone, 26,000 light years at the speed of light, means that any message they send home will take 26,000 years to arrive. They cannot go home in any meaningful sense. Relativistic travel at extreme speeds is a one-way journey into the deep future, a permanent exile from the world of one's origin. This is the dual nature of time dilation as a solution to the interstellar travel problem. It solves it for the traveler, but not for the civilization. The traveler can experience cosmic distances in a human lifetime, but they do so at the cost of permanent disconnection from their home, their time, their people. The energy requirements for relativistic travel are equally sobering. The kinetic energy of a spacecraft increases dramatically as it approaches the speed of light. At 10% of the speed of light, the kinetic energy of a 100-ton spacecraft, which is much lighter than the International Space Station, is about 4.5 times 10 to the power of 21 joules. This is approximately equal to the total energy consumption of the entire world for about 30 years. At 90% of the speed of light, the kinetic energy of the same 100-ton spacecraft rises to about 47 times 10 to the power of 21 joules, or roughly 300 years of world energy consumption. At 99.9% of the speed of light, the kinetic energy approaches 10,000 years of world energy consumption. These energy requirements do not change with the propulsion technology used, regardless of whether the energy comes from chemical rockets, fusion drives, antimatter annihilation, or laser sails. The same kinetic energy must be imparted to the spacecraft. The propulsion technology affects only the efficiency with which that energy is applied to acceleration. Antimatter is the most energetically efficient propulsion technology permitted by known physics, but even an antimatter rocket would require a quantity of antimatter equivalent to a significant fraction of the spacecraft's final mass to reach relativistic speeds. Let your breathing be slow and steady. In, gently, and out, completely. We are exploring the edges of what is permitted by the laws of physics as we currently understand them. These numbers are not pessimistic speculations. They are the straightforward consequences of special relativity and energy conservation, two of the most thoroughly tested theories in physics. There is one more concept to explore before we settle fully into rest: the interstellar medium and its dangers at high speeds. The space between stars is not truly empty. It contains a very diffuse gas, primarily hydrogen, at densities of about 1 atom per cubic centimeter in the vicinity of our solar system. At the speeds we are discussing, this tenuous gas becomes a significant hazard. A spacecraft traveling at 10% of the speed of light, 30,000 kilometers per second, encounters each hydrogen atom not as a slow particle to be deflected gently, but as a high-energy particle that can damage spacecraft materials and electronics. At 99% of the speed of light, the protons of the interstellar medium would strike the spacecraft with energies comparable to cosmic rays, creating showers of secondary particles and causing radiation damage to any biological passengers and to electronic components. A spacecraft traveling at these speeds would need extraordinary radiation shielding, either from the front in the form of a very dense shield of material that ablates as it absorbs impacts, or through magnetic deflection of charged particles, similar to the way Earth's magnetic field deflects solar wind. The design of adequate shielding for relativistic interstellar travel is an active area of theoretical engineering research. Additionally, a spacecraft at high speed will encounter occasional larger particles, dust grains of micrometer or millimeter size, with devastating effects. A sand grain impacting at 90% of the speed of light carries an energy comparable to a small bomb. The interstellar medium, while incredibly diffuse by terrestrial standards, is not completely dust-free, and at the relevant speeds, even very rare impacts could be catastrophic. This problem requires either extremely robust shielding, which adds mass, or a leading shield that sweeps the path clear, perhaps using magnetic fields or focused laser beams to vaporize incoming particles. Another concept that has appeared in serious scientific literature, though it requires physics that may or may not be correct, is the Alcubierre warp drive. In 1994, the Mexican physicist Miguel Alcubierre showed that general relativity permits, at least mathematically, a space-time metric in which a region of flat space-time is enclosed in a bubble that moves through space faster than light by compressing space in front of the bubble and expanding it behind. A spacecraft inside the bubble would experience no local violation of special relativity because it is stationary within its local flat spacetime. The bubble itself moves at superluminal speed, but nothing within the bubble violates the speed of light limit locally. The Alcubierre metric requires exotic matter with negative energy density, a form of matter that violates the weak energy condition and has not been demonstrated to exist in macroscopic quantities. The energy requirements of the original Alcubierre metric were calculated to be unphysically large, greater than the total mass energy of Jupiter. Subsequent refinements have reduced the theoretical energy requirement, but it remains unclear whether practical warp drives are physically realizable or whether the exotic matter they require can exist in the necessary forms and quantities. The Alcubierre metric is a genuine solution to the equations of general relativity, but whether it describes a realizable physical situation is unknown. What would a spacecraft actually find if it reached another star system in a human lifetime. The nearest stellar neighborhood contains a remarkable diversity of objects. The Alpha Centauri system, 4,037 light-years away, consists of two sun-like stars, Alpha Centauri A and Alpha Centauri B, orbiting each other over a period of about 80 years, and a small red dwarf called Proxima Centauri, orbiting much farther out with a period of about 550,000 years. Proxima Centauri is currently the nearest star to the Sun by a small margin. It hosts at least one confirmed planet, Proxima Centauri B in the habitable zone, and at least one additional candidate planet. Alpha Centauri A and B may also host planets. Though detecting Earth-sized planets in a binary system is observationally challenging. Tau Ceti, about 11.9 light-years away, is a sun-like star with at least 4 planet candidates, 2 of which orbit in or near the habitable zone. At 90% of the speed of light, Tau Ceti could be reached in about 5.8 years of ship time. 61 Cygni, a binary system of 2 red dwarf stars about 4 light-years away, was one of the first stars to have its distance measured by Friedrich Bessel in 1838. Epsilon Eridani, about 10.5 light-years away, is a young sun-like star with a debris disk and at least one planet. At 50% of the speed of light, all of these systems would be within reach in less than 30 years of ship time, within a single career-length period of human life. At 90% of the speed of light, dozens of star systems out to 100 light-years could be visited in less than a human lifetime. Each of these systems represents a potential new world, a new set of planets, new surfaces, new atmospheres, new chemistries, and possibly new life. The deepest question raised by this exploration is not the engineering question of how to build a fast enough spacecraft. It is the human question of what it means to leave and what drives us to leave. The history of human exploration is a history of crossing distances that previous generations regarded as uncrossable. The first humans to cross from one continent to another on foot, following game herds across land bridges, were crossing distances that their ancestors had never crossed. The Polynesians who settled the Pacific Islands navigated thousands of kilometers of open ocean in double-hulled canoes, guided by stars and wave patterns and the behavior of birds, reaching islands that no previous human civilization had known existed. The European voyages of the 15th and 16th centuries found continents that half the world did not know were there. Every expansion of the human horizon was made possible by technology and courage and curiosity, and every expansion revealed not a barren emptiness, but new richness, new diversity, new possibility. Interstellar travel is the next horizon. It is the horizon beyond which we cannot currently see with enough clarity to know what lies there. We know the distances, we know the physics, we know the stars that are waiting. We have already detected dozens of planets around the nearest stars, some of them potentially habitable. We know how long it would take to reach them at various speeds. We do not yet know how to achieve those speeds, or whether we can, but knowing the physics of what is possible, even in principle, changes the nature of the question from whether to how and when. A person born today, if they live to 80 years of age, and if a fusion-propelled spacecraft or a laser sailcraft or some other technology we have not yet imagined became available during their lifetime, might in principle participate in or witness the first steps toward interstellar travel. Not the journey to Alpha Centauri itself, which would take decades or centuries even with advanced propulsion, but perhaps the first laser sail probes, the first experimental fusion drives, the first demonstration that the physics of relativistic travel is achievable rather than merely theoretical. The first radio telescope message to a nearby star. The first detection of a biosignature in an exoplanet atmosphere that cannot be explained by geology alone. These are not guaranteed events. They are possible futures, grounded in real physics, awaiting real decisions about investment and effort and political will. The universe will not bring the stars closer, but the tools we build and the physics we understand might in time make the distance feel less absolute and the journey feel more possible than it does tonight. Let your body be still now. Let your breathing be slow and quiet and easy. The nearest stars are 4.37 light years away, and the physics of reaching them, while enormously challenging, is not forbidden. The universe permits faster travel than we have achieved, up to speeds approaching the speed of light, governed by the same equations of special relativity that GPS satellites rely on every day. The time dilation that makes relativistic travel subjectively manageable is real, measured in muons, in atomic clocks, and particle accelerators. The energy required is vast but finite, potentially available through nuclear fusion or antimatter or technologies not yet imagined. Before we settle into the final quiet, there is more of this extraordinary question to explore. The universe has its own answers to the propulsion problem, and some of the most fascinating engineering concepts proposed for interstellar travel draw on ideas that are as elegant as they are ambitious. The Bussard ramjet is a concept proposed in 1960 by the physicist Robert Bussard that has captured the imagination of science fiction writers and physicists alike for decades. Bussard proposed a spacecraft equipped with an enormous electromagnetic scoop, perhaps thousands of kilometers in diameter, that would collect hydrogen from the interstellar medium and funnel it into a fusion reactor at the front of the ship. The hydrogen would be fused, releasing energy that would be directed rearward as exhaust to produce thrust. The appeal of the concept is that the fuel is collected continuously from the interstellar medium itself, eliminating the need to carry propellant on board. In principle, a Bussard ramjet could accelerate indefinitely, approaching the speed of light and maintaining it without ever needing to refuel. There are serious physical problems with the Bussard ramjet as originally conceived. The density of hydrogen in the interstellar medium is very low, about 1 atom per cubic centimeter, meaning the scoop would need to be enormous to collect enough fuel for meaningful thrust. At high speeds, the drag from the electromagnetic scoop interacting with the interstellar plasma might exceed the thrust produced. The proton-proton fusion chain, which the interstellar hydrogen would need to undergo, is extraordinarily slow and difficult to achieve in a controlled setting, unlike the deuterium-tritium or deuterium-helium-3 reactions considered for fusion rockets. Later analysis by physicists, including John Ford and Carl Sagan, showed that the original Bussard ramjet would likely decelerate rather than accelerate in realistic interstellar medium conditions. However, modified versions of the ramjet concept, sometimes called catalytic ramjets or ram-augmented interstellar rockets, that carry their own fusion fuel but use collected interstellar hydrogen as additional propellant or as reaction mass may be more physically viable. The concept remains a stimulus for creative engineering, thinking about how to take advantage of the material that exists in the interstellar medium rather than treating it purely as an obstacle. Generation ships are perhaps the most often discussed alternative to ultra-fast interstellar travel. If a spacecraft cannot travel fast enough to reach another star within a single human lifetime, perhaps it could carry multiple generations of humans, with the descendants of the original crew completing the journey after centuries of travel in a self-contained artificial world. A generation ship would be a spacecraft large enough and complex enough to support a viable human population indefinitely, with its own agriculture, recycling systems, social structures, governance, education, and psychological environment. The engineering requirements for a generation ship are formidable. A stable, self-sustaining ecosystem capable of supporting hundreds or thousands of people requires extraordinary complexity and redundancy. Food production through hydroponics and aquaculture, atmospheric recycling through biological and chemical systems, water purification, waste processing, energy generation and storage. Medical facilities capable of treating any condition that might arise over centuries of travel, including surgery, childbirth, and the management of chronic and infectious diseases, and the manufacture and repair of all critical systems using only materials available on board. The population of a generation ship must also be sufficient to maintain genetic diversity. Genetic studies of human populations suggest that a minimum viable population for a long-term isolated community without significant genetic drift causing health problems over many generations is somewhere in the range of a few hundred to a few thousand individuals, depending on assumptions about the selection and reproduction patterns in the community. Too small a founding population leads to inbreeding and the accumulation of harmful genetic variants. Managing the genetics of the ship's population over centuries of travel would require careful planning and possibly artificial selection or gene therapy. The social and psychological challenges of a generation ship may be even more formidable than the biological ones. A closed community of hundreds or thousands of people, unable to leave, unable to receive meaningful external communication, knowing that their journey will outlast their lives and the lives of their children, faces extraordinary psychological pressures. The meaning of the mission must be transmitted across generations from people who chose to embark to their children, who did not choose to be born into this situation, and their grandchildren who may be separated from the original departure by more generations than they can comprehend in personal terms. Maintaining cohesion, purpose, and functioning governance structures across centuries of isolated travel is a problem that has no historical precedent. The largest isolated communities in human history, island civilizations like those of the Polynesian Islands, were still embedded in a natural environment that provided external stimuli, weather, seasons, the sea, wild animals. A generation ship would be entirely artificial, its environment entirely managed, its sky entirely constructed. Some proposals for generation ships address the psychological dimension by designing the ship as a world as rich and varied as possible, with large biomes, simulated landscapes, and spaces that encourage a sense of connection to nature. The ship might be constructed as a rotating cylinder or torus, with centrifugal force substituting for gravity and the interior curved into a coherent landscape of forests and fields and waterways and weather under artificial sky. Such designs, sometimes called O'Neill cylinders, after the physicist Gerard O'Neill, who popularized the concept in the 1970s, are structures of enormous scale and complexity, beyond any engineering achievement yet undertaken, but not physically impossible. Hibernation and suspended animation offer a possible alternative to the multi-generational ship. If humans could be placed in a state of dramatically reduced metabolism for the duration of an interstellar journey, either through controlled hypothermia, through pharmacological suppression of metabolism, or through some more exotic biological or technological means, they could in principle be transported in a state of biological stasis and revived on arrival. The crew would age little or not at all during the journey, regardless of how long it takes in external time. The biology of hibernation is well understood in many animal species. Bears, hedgehogs, ground squirrels, and many other mammals hibernate through winter, reducing their body temperature, heart rate, and metabolic rate dramatically for months at a time. The mechanisms of mammalian hibernation involve complex cascades of gene expression changes, modifications to enzyme activity, and alterations in the sensitivity of cells to cold and hypoxia. Some researchers believe that the molecular mechanisms of hibernation could in principle be induced in humans either through pharmacological agents or through genetic modification. Arctic ground squirrels, one of the deepest hibernators among mammals, can reduce their body temperature below the freezing point of water, surviving internal temperatures of about -3 degrees Celsius through supercooling of body fluids, which prevents the formation of ice crystals that would damage cells. Their heart rate drops to about 1 beat per minute, and their metabolic rate falls to about 2% of the active rate. They can maintain this state for 8 months of the year. Human hibernation, even if achievable, would need to be maintained for years or decades rather than months, a quantitatively and qualitatively different challenge. Cryonics, the practice of preserving humans at very low temperatures with the intention of reviving them in the future, is a distinct and currently speculative approach. Existing cryonics organizations preserve recently deceased or legally dead individuals at liquid nitrogen temperature, 196 degrees below 0 Celsius, with the intention that future technology might revive them. The primary challenge of cryonic preservation is ice crystal formation during freezing, which damages cells mechanically. Modern cryonics uses cryoprotectant chemicals to reduce ice formation in a process called vitrification, producing a glassy solid rather than a crystalline ice structure. Whether vitrified tissue can be revived without damage, and whether the information encoded in the structure of the brain, which is the basis of consciousness and memory, survives vitrification, are unresolved questions. Synthetic biology and genetic engineering may eventually provide tools for inducing controlled reversible suspension states in humans that do not exist in nature. Understanding the molecular mechanisms of hibernation well enough to engineer them into non-hibernating mammals, including potentially humans, is a plausible long-term research direction. The medical applications alone for preserving critically ill patients, for extending the window of treatment and trauma, for long-duration spaceflight within the solar system, would be enormous incentives for this research regardless of its interstellar implications. As we think about what a traveler at relativistic speeds would actually experience, it is worth considering the visual phenomena of near light speed travel, which are among the most extraordinary predictions of special relativity. At high speeds, an effect called relativistic aberration causes stars to appear to cluster toward the direction of travel. Light from stars in front of the ship is blue shifted, meaning the photons are compressed to shorter, more energetic wavelengths, while light from stars behind the ship is red shifted, stretched to longer, less energetic wavelengths. At 90% of the speed of light, the stars in front of the ship would appear bright and blue, while the sky behind would appear dim and red. At speeds approaching the speed of light, almost all the starlight would appear concentrated in a bright ring directly ahead of the ship, a brilliant circle of blue-white light surrounded by near total darkness. This effect, combined with the radiation from impacting interstellar particles, means that the visual experience of near light speed travel would be deeply strange and alien, nothing like the familiar star field of science fiction. The universe would not look like the night sky. It would look like something for which we have no reference. A concentrated blaze of distorted light in one direction and an expanding darkness behind. The question of what to do upon arrival at another star system is as fascinating as the question of how to get there. A crude interstellar mission would presumably carry scientific instruments, biological specimens, and possibly seeds, embryos, or genetic material sufficient to establish a permanent human presence, as well as equipment for constructing shelter, extracting resources, and communicating with Earth. The first generation of interstellar travelers would be simultaneously astronauts, scientists, engineers, doctors, farmers, and founders, responsible for establishing the first foothold of human civilization beyond our solar system. If a planet of the destination star were found to be uninhabited, the colonization question is primarily one of engineering and survival. If a planet were found to bear life, including potentially microbial life, the question becomes far more profound. The discovery of extraterrestrial life, even simple microbial life, would fundamentally transform our understanding of the cosmos and our place in it, and the question of whether to colonize a planet already bearing its own biosphere, even a simple one, raises ethical questions that human civilization has never had to confront. The ethics of interstellar colonization are genuinely novel. Terrestrial colonial history provides cautionary tales about the consequences of powerful civilizations arriving at inhabited territories. The biological contamination question is also crucial. Would Earth life introduced to an alien biosphere compete with native organisms, outcompete them, or die in the alien environment? Would alien microorganisms carried back to Earth have devastating consequences for Earth's biosphere? The early history of the European colonization of the Americas where introduced diseases killed the majority of the indigenous population within a century of contact, provides a sobering precedent for what happens when two biospheres that have evolved independently come into contact. Humanity has developed some framework for thinking about planetary protection through the work of the Committee on Space Research, COSPAR, which has established guidelines for preventing biological contamination of other bodies during robotic space missions. These guidelines would need to be greatly expanded and applied with unprecedented rigor to any crewed mission to a potentially inhabited world. Let your thoughts drift quietly. The stars are patient. The questions will be there when the generations come who must answer them. And tonight, the relevant question is simply this: could a human being, born in a time not too far from our own, travel far enough through space in a single lifetime to see another sun rise over another world? The honest answer, grounded in the physics we know, is maybe. Not certainly, not soon, but possibly in a future measured in decades rather than millennia, if the right investments are made, if controlled fusion power is achieved, if laser sail technology is developed, if the political will to attempt interstellar missions exists. The universe does not forbid it. The physics allows it. The nearest stars are reachable in a human lifetime at speeds that are theoretically achievable with technologies grounded in known physics, not speculative future discoveries. And even at current technology, not in a lifetime, but in a century, a robotic precursor mission could reach the Alpha Centauri system, send back images of its planets, confirm whether any are habitable, and return data that might determine the next centuries of human space exploration. We are not at that point yet, but we are closer than we have ever been, and the physics has been worked out. How far could humans actually travel through space in one lifetime? At the speed of physics, very far indeed. At the speed of current technology, not far at all, and somewhere between those two limits lies the future, waiting to be built. Sleep now. The stars are where they have always been, patient and bright, burning in the dark. Alpha Centauri is 4.37 light-years away tonight. It will be 4.37 light-years away when you wake. The physics of reaching it is real. The distances are real. And the question of how far you could travel in a lifetime is one of the most beautiful questions physics has ever permitted humanity to ask. Consider for a moment what it means that we can ask this question at all. 100 years ago, we did not know that other galaxies existed. We did not know that other stars had planets. We did not know that the universe was expanding. We did not know about dark matter or dark energy. We did not know the age of the universe to within a factor of 10. The knowledge that makes the question of interstellar travel meaningful, that makes it a question of physics rather than pure speculation, has been assembled in the span of a single long human lifetime. The equations of special relativity, written by Einstein in 1905, are barely a century old. The confirmation that the universe contains billions of exoplanets is only a decade old. The detection of gravitational waves, which opened a new observational window on the universe, is less than a decade old. We are a young species on the scale of the cosmos, and a young scientific civilization on any scale at all. The knowledge we have accumulated in 400 years of modern science would fit in a small library compared to the vast, uncharted territory of what remains to be discovered. The physics of interstellar travel that we have explored tonight, the relativistic time dilation, the energetics, the propulsion concepts, the hazards of the interstellar medium, represents the current frontier of what is known. Beyond that frontier, as beyond every frontier in the history of science, lies more, waiting for patient minds and careful instruments in enough time. You are resting tonight on the only world humanity has ever called home. Above you, past the ceiling, past the atmosphere, past the orbiting satellites, past the moon, past the sun and all its planets, the stars are burning. Alpha Centauri is burning in the southern sky, unreachably close by cosmic standards, reachable in principle by the physics of relativity, and reachable perhaps in practice by the ingenuity of generations not yet born. The Milky Way is turning slowly overhead, its 100 billion stars each a sun, many of them with worlds. And the question of how far a human could travel in a lifetime is not merely an engineering question. It is a question about the future of everything consciousness has ever valued: curiosity, discovery, the desire to know what lies beyond the next horizon. That desire is part of you tonight. It is part of what made your ancestors walk across continents and oceans to find new lands. It is part of what made someone look up at the night sky 100,000 years ago and wonder what those lights were. It is part of what drove Galileo and Newton and Einstein and Hubble and all the generations of scientists who assembled the knowledge we carry tonight. And it will be part of what drives the people who, in some future, whose exact shape we cannot yet see, will answer the question with action rather than calculation. Rest now. The universe holds the question safely until morning. The stars are patient. The physics is real. And you, in this quiet moment, are part of the long, unbroken thread of minds that have looked up and wondered and refused to accept that the horizon is the end of the world. Good night.